So we have one final presentation, Bhavna, is that right?
Yes. Coming
By the
to the
way,
last presentation of the day by Himanshu, Saurabh, and Aayush. It's called FineSpine App, a tool to help doctors and technicians detect spine fractures, and a web application intended to assist doctors and technicians detect spine fractures in patients.
Hi everyone, I'll be sharing my screen. I hope it's visible. Okay, Aayush, you can start.
Good evening, everyone. Me, along with my team, FineSpine, are going to present our project on cervical spine fracture detection. Next slide. So first things first, let's talk about data science and healthcare in general. Data science is used in multiple domains in healthcare, like drug discovery, for the synthesis of new drugs using AI, for chatbot assistance, and for live data tracking and handling huge amounts of data. With the help of the application of data science, it has now become possible to detect symptoms of a disease at a very early stage. Also, with the advent of various innovative tools and technologies, doctors are able to monitor patients' conditions from remote locations as well. It can also be used for predictive imaging by learning disease patterns, which is related to our particular use case. Next slide. So to talk about our problem specifically, there are 1.5 million fractures that occur annually, and that is only in the US, of which 15% are in the cervical spine region, making it the third most common traumatic injury in elderly people. Next slide. So what is the cervical spine? As you all know, the human spine is made up of 33 bones called vertebrae and has 5 major regions, namely cervical, thoracic, lumbar, sacral, and the coccyx region. Of these, the cervical spine consists of the 7 top vertebrae which support the head and the neck. Next slide. So how can we inspect the cervical spine in the event that there actually is a fracture? The solution is through medical imaging. Medical imaging is nothing but creating visual representations of certain relevant systems of the body. It includes types like MRI, CT, ultrasound, and X-ray. Of these, the CT scan is considered to be the most informative as it combines a series of X-rays along multiple cross-sections, as will be shown later, to better focus at the area of concern. I'd like Saurabh to continue.
Thank you, Aayush. So to give you an overview of our approach, let's start with the data. Our data consists of 2019 CT scans obtained from the Kaggle RSNA challenge. Data from the CT scans were extracted in 2 formats. The first is a DICOM file and the second as a NIFTY file. These formats can be considered as normal images, just with patient data such as name, age, gender, study details such as the name of the physician, the time of the study, as well as the device details such as the name, manufacturer, and scanner details. The primary distinction between these 2 file formats is that DICOM file stores images in a 2D format with multiple slices, whereas NIFTY files are stored as a single 3D image. Furthermore, we have observed that NIFTY files capture bone density better, but due to the lack of data, we chose to stick to DICOM files for our use case. As shown on the left graph, our data is fairly balanced for identifying spine fractures as a whole, but is severely unbalanced for classifying individual fractured vertebrae, as shown in the right. So how would our app work? Assume a patient comes in for a CT scan. The machine would scan the patient's spine on the axial plane, as depicted in the video. From the scan, we get the DICOM slices, and we would then concatenate and transform them to create the patient's cervical spine in 2D format. This 2D format image is then fed to a convolution network architecture, which predicts whether the patient's cervical spine is fractured or not. So let's get on to our results. We tested a number of custom and pre-trained CNN architectures to predict the fracture. We zeroed in and built our application using the ExceptionNet model architecture because it provided the best prediction with consistency and good model explainability, which we'll see in our app demo. Over to Himanshu for the app demonstration.
So the FineSpine app is made using React as a front end to make it more interactive, and Fast API for backend because it is a Python-based framework and our model can be easily integrated in it. And we have used GCP, GK, Google Kubernetes cluster to make it more scalable. We have done the whole deployment using Ansible, as we don't have to go to GCP website and provision all the compute and storage. Ansible does the job for us. Enough of this. Let's go towards the app. So as you can see, this is the upload page. I'll be uploading a scan. So I'll choose a scan, open it, and I'll give it a patient ID. Let's say 2222 and submit it. So it may take a while to submit. While it is submitting, let me explain to you like how the process works, like how from front end to back end to Google storage the file goes. So first of all, as you click on the submit button, the backend fetches both the patient ID as well as the file. And after fetching both of these, it takes the zip file and extracts it. After extracting the zip file, it will contain all the segments of the images. So your scan has a lot of segments and convert those segments into a sagittal view of image. And then this sagittal view of image is then passed to the Google storage, which is Google Cloud Bucket, and stored with the same name as the patient ID. So in this case, it will be 2222. As you can see, the file is being successfully processed and uploaded. Let's go for prediction. So let me put the number 2222 and submit it. So again, here what happens is the backend is taking the number 2222 and searching it in the GCP storage. And if it gets the image, and so it fetches the image, and then it passes that image through our CNN model. Now, instead of giving the fracture probability, what we are giving is these boundaries. So these boundaries are actually heat maps boundaries, which shows the most likely fracture area. So this, and we are not providing any density of color so that it will help a radiologist to view it. So guys, what we have here is an app which helps the radiologists to detect cervical spine fracture. And in case you have a lot of files, let's say thousands of scans, it can help prioritize which patients have severe fracture compared to which don't have. With this, I would like to stop my presentation. Thanks a lot. And if you have any questions, feel free to ask.
All right. Thank you, Tim. This is fantastic and useful. Let's ask a few questions. I see Supreet. You have your hand up. Go ahead.
So my question was, how accurate is your app? Have you tried with any other CT scans to see its accuracy and then took a professional advice to see its accuracy?
If I can take over. So we did experiment with a lot of architectures, and right now, even if you see our model results, it's not the perfect one. I would not say it's the best yet, because we did participate in the Kaggle competition itself. We are nowhere in the top hundreds itself. The best architectures are quite complex using multiple approaches. Now, this would be something that we will work on, like fine-tune the model, use different architectures using, because like I told you, Nifty files and DICOM files. Nifty files are you can get a very accurate representation of a bone. Right now, if you see our explainability, you can see muscles and all other ligaments as well. Nifty files will give you that proper bone, the scan. But due to the lack of data, we weren't able to do that. And getting medical images is quite difficult.
Okay.
Also, to add to Saurabh's answer, we also saw a lot of approaches which uses MONAI and other transformations for masking bone and all, but those things were not implementable in our backend because the file was very huge. So to make it edge friendly, we went with simple models for now, and we in future, we have thought of incorporating them, but again, those seems a very far stretch for us right now.
Oh, okay. Thank you.
I had a follow-up on that, Saurabh. So you said the accuracy, based on the accuracy, it kind of shows those lines, right? So what was the cutoff or the threshold you?
For the explainability, the cutoff is quite high. Like we keep it somewhere in the 90s itself.
Okay. No, the
Yeah.
reason I was asking that was that could answer like Supreet's question is if I had a way to change that to like say 99%,
Yeah.
then it becomes very specific, right? So that
Yes.
like that's something maybe you can change or
Yeah. And additionally, we only like it's an active choice that we haven't given a prediction whether it's a fracture or not, because we don't aim to replace the doctor. We just provide you the explainable region so that then they can actually see the image and decipher is it a fracture or not.
All right,
Okay,
thank you.
all right. Well,
Shivas?
no,
Go ahead.
one more question I was thinking was you told us about the size of files. So, and I know were thinking about future work. So have you considered rather than the upload, like direct integrations with these MRI software systems? Because these files I know can go to like gigabytes, right? So like a direct connection and then maybe pre-process at source and then only send something what your model needs or something like that.
Yes, exactly. Like the data right now that we have used is around 300 GB and it was only like 2000 patient scans. So yeah, each file is around 300 MB. That's why our upload also takes time. But yes, this is actually a good way that we can upload it from the source itself. Like everything could be like a hospital application that the hospital can then use to upload as well as predict.
Yeah, thank you, guys. I think this is a good segue to just put some final thoughts in the sense that it's not always about the accuracy of the model, the usability too. Something we at Univ.AI we're trying to do is, first of all, you understand the models all the way to the bottom, but you're able to deploy them. And I think that the final presentation showed that it's not only about Kaggle competitions and getting the good score. It's just, can you make this into something that is useful? Actually, a study recently, when Shivas and I put this course together, shows that only 10% of AI is ever been seen by a user, and that's one of our goals here. We have seen kind of the diversity of the projects we have from the students, from, I don't know, music to storytelling to spine detection to search engines. This is quite diverse, but I think the theme is there. Can we understand the models? Can we go down deep into the mathematical understanding of the models, put it together, test it, and then deploy it?